All right, in this video, we're going to look at what are called the tangential and normal components of acceleration. This is the last major topic in this chapter, and so it's really just relating some things that we've actually done before. So if you look at what this is called, you'll see that we're talking here about something about the acceleration vector, and we want to think about the tangential and normal components of that acceleration vector. So we're relating that acceleration vector to the tangent and normal vectors. So that's the idea of what we're doing here. All right, so we're going to just build this up based on some things that are prior definitions and prior formulas that we have talked about previously in this chapter. All right, so what we want to start with is our acceleration vector and relate that to these other two vectors here. So we're going to start with the definition of the acceleration vector. So you should know that one pretty well. The acceleration vector is just the derivative of the velocity vector with respect to time, or second derivative of the position vector. Right? So that is from some previous definition. And what we want to do now is relate that to the tangent and normal vectors. So we need to make a connection here between what we've got here and these two vectors. So we're going to start by thinking about this velocity vector and thinking about how that relates to these vectors here. So you might remember that for a smooth parameterization, so as long as r of t is a smooth parameterization, the unit tangent vector is given by the derivative of the position vector, or the velocity vector, divided by its magnitude. Right? So that is from what we did previously when we talked about the unit tangent vector. This is how you calculate the unit tangent vector most of the time. And so as long as we have a smooth parameterization, this equation is valid. So what I'm going to do here is just rearrange this equation a little bit and solve for the velocity vector. So I can replace that here in this expression here. So I'm just going to multiply both sides of this equation by the magnitude of the velocity vector. And so we have this relationship here. All right, so what I'm going to do now is take this expression here, the velocity vector, magnitude of the velocity vector times the unit tangent vector, and I'm going to put that into this definition in place of that v right there, since that's equal to v. Okay, and then as we go through this, we're going to just let the symbols tell us what to do. I'm going to say that to you often in this class, let the symbols tell you what to do. And so some of that is making sure that you're comfortable with those symbols and that you can hear what they're telling you to do. So here, this d dt, that is a differential operator. It's telling us to take a derivative with respect to t of this v vector. So we're going to replace the v vector with this expression here. So we've got derivative with respect to t of magnitude of the velocity vector times the unit tangent vector. Okay? So now we're just going to do what that is. Remember that these are probably functions, and so we're taking a derivative with respect to t of those functions. So we have a product rule for differentiating with respect to t. So I'm just going to do my product rule here. So the derivative with respect to t of the first function. So d dt of magnitude of the velocity vector times the second object in my product here, plus the first object times the derivative with respect to t of the unit tangent vector. I'm just going to write it like that. Okay, I've used slightly different notation here for derivative with respect to t of this magnitude of the velocity vector. I left that differential operator outside. And here, when I have derivative with respect to t of the unit tangent vector, I wrote it in this way. So those are both just different representations of the same thing. Part of the reason I did that is that I want to do something like what I did up here. And we're going to take the unit tangent vector, and we're going to replace this expression here. So in the same way I replaced the velocity vector up here, we're going to replace this expression with something. So when we think about what we're going to replace that with, remember that our idea here was that we wanted to relate the acceleration vector to the unit tangent and unit normal vector. And you can see right here we've got the unit tangent vector right here, but we do not have the unit normal vector in here somewhere. There is, however, a relationship between the unit normal vector and dt dt. So remember that the unit normal vector, so similar to what I did here, I'm going to do again, but for the unit normal vector, that unit normal vector, as long as you have a smooth parameterization, is calculated by finding t prime, or I'm actually going to use this notation instead of t prime. So t prime, the derivative of the unit tangent vector, divided by its magnitude. Okay, so just like I did over here, I'm going to take that quotient and rearrange that a little bit. So I'm going to multiply both sides by the magnitude of dt dt. So magnitude of dt dt times that unit normal vector is dt dt. Let's just rearrange this. And then the idea here is that I then want to take this expression and substitute it in here in place of what that is equal to. Okay, so I'm going to go ahead and do that. And then we will essentially have what we were after. Okay, so this part, I'm just copying down. And then here, on this term, I'm going to replace dt dt with magnitude of dt dt times the unit normal vector. I'm also going to do a little regrouping here. So I will have magnitude of v times this product. And so that's all multiplication. I'm just going to use my associative property of multiplication to rewrite that. So I've got some different things kind of grouped together here. So I'm going to have my magnitude of the velocity vector from here. And then in place of dt dt, I'm going to put this magnitude of dt dt times my unit normal vector. And I'm going to insert a grouping symbol here. These are all multiplied times each other. I put that grouping symbol there to just emphasize this idea of what we were after here, relating that acceleration vector. So all this is the acceleration vector. And the idea is that I've now related that acceleration vector to the unit tangent vector and the unit normal vector. And that's what we were really after. So here we've actually done all of the work to define this. It's just a matter of kind of giving some names and some notation to this and talking about what this means. What we see here when we think about what this means, we've got that the acceleration vector here, this is a vector, is equal to, this part in this first group here is a scalar function perhaps, but we've got a magnitude of a vector function and then a derivative with respect to t of this. So this is a scalar times a vector plus, and then here again we have another scalar function probably, but this is another scalar. And so what we have here is our acceleration vector written as a sum of scalar multiples of the t and the n vector. So we have decomposed or broken that acceleration vector down into how much of that is in the direction of the t vector and how much of that is in the direction of the n vector. And that's what we mean when we talk about tangential and normal components of acceleration. I'm going to go ahead and write down the definitions down here. This scalar quantity that's times the unit tangent vector is what we call the tangential component of acceleration. And we denote that A with a subscript of t. This is a scalar quantity. So this scalar derivative with respect to t of the magnitude of the velocity vector. Notice this is rate of change of speed with respect to time. That's the tangential component of acceleration. That's how that's defined. And then this quantity over here is the normal component of acceleration, a sub n, and that's defined to be this scalar quantity here. You do not need to memorize these formulas. There are a few formulas provided on your unit exam, and these are 2 of them. They're provided on there, so you don't need to memorize those. It is helpful to understand what they mean. I do not expect you necessarily to recreate this kind of derivation, but I do want you to understand that that acceleration vector, I've just used prior definitions and done the differentiation that it says here to do. And so understanding how this is derived, so understanding the logic behind it, and then understanding what these 2 quantities describe here. So these are both scalar quantities. You might notice from looking at how they're defined, whether they could be positive, negative, or 0. Let's start with a sub n here. A sub n is the product of 2 magnitudes of 2 vectors here. So this scalar is only ever going to be 0 or bigger, and this scalar is also only ever going to be 0 or bigger. So a sub n is a scalar, but it will only ever be greater than or equal to 0. It won't ever be negative. The tangential component of acceleration here, this is a derivative with respect to t of speed, right? Magnitude of a velocity vector is speed. So this is a rate of change of speed. So a derivative can be positive or negative or 0. And depending on whether it's positive or negative or 0, that tells you something about the motion of the object. We'll look at that when we look at some examples too. But this scalar can be positive, can be negative, or can be 0 for this scalar. This one only is greater than or equal to 0. All right, the only thing left to do that I want to talk about in this video is just a little picture kind of illustrating what's going on here. And there are really many pictures I could draw, so you don't want to get stuck on the one picture that I draw here. But the idea is that if you have some object moving along a curve, we'll give it an orientation there. So an object moving along a curve, we've got a unit tangent vector to the curve. So whatever one unit of length is, at some point I can estimate a unit tangent vector, 1 unit long, and along the motion of the curve. And then a normal vector to the curve, 1 unit long, perpendicular to the tangent vector and on the concave side of the curve. So there are just some sketches, little estimates of a t and n vector at that point. And then the idea that I want to think about here, so even if those don't look like a right angle, we're going to know that they should be a right angle there. What I want to think about here is the acceleration vector. So as an object is moving along that path, its acceleration vector at that particular point, what this tells us is that that's got to be a sum of scalar multiples or a linear combination of the t and the n vector. This part here can only be greater than or equal to 0. The tangential component of acceleration could be positive, negative, or 0. I'm going to draw a picture here where the tangential component of acceleration is positive, and then we'll talk about what that means about the motion. So when the object is at this point on the curve, perhaps my acceleration vector would be going like this. I cannot tell just from looking at the curve where that acceleration vector would be or how long it would be, because that's about the motion along the curve. T and n, remember, about the geometry of the curve, so I can draw an estimate of those just from looking at the picture here, as long as I know a scale of 1 unit of length. The acceleration vector, though, has to do with when an object is moving along that curve. Is it speeding up? Is it slowing down? Is it going at a constant speed? So all kinds of different things here. So the picture, though, the idea here is we've done this when we looked at vectors and we decomposed a vector into a sum of scalar multiples of 2 other vectors. Essentially what we're looking at there is a projection of this acceleration vector along the t vector, and then a projection of that acceleration vector along the n vector, which would be here or also here. So this length of this side here is the an, so how much that acceleration vector is lined up with the n vector. And then this distance here, which remember could be negative, but is not in my picture here, would be the tangential component of acceleration. So how much of that acceleration vector is lined up with the t vector. That might preview some alternate formulas here. We did projections of one vector onto another vector and dot products and cross products to find different sides of a right triangle here. So some of the alternate formulas refer back to those vector properties that we used before. But the main thing here is just understanding what these things describe, how much of that acceleration vector is lined up with the t vector, and or how much of that acceleration vector is lined up with the n vector, and then what those answers mean in terms of the motion. We'll look at some alternate formulas and some examples in some later videos so you can get a feel for actually calculating these things.